Yes, welcome everyone to the now last talk of this season before the summer break. I'm very happy to introduce Zihang Qiu. He's a PhD student at the University of Amsterdam. He received his master degree in physics from ETH, and he's quite an exceptional person in the operations research or optimization field because he's working on the intersection of the medical field and optimization. So he's on a joint project with Harvard Medical School and the Massachusetts General Hospital, and his research focus on uncertainty in proton radiation therapy. I'm happy to have you here, Ziang. Please
Yeah,
go ahead.
yeah. Thank you, Yanis, for your introduction. Yeah, so without further ado, today I'm presenting a project on K-adaptability approach to proton radiation therapy, robust treatment planning. And as you can see, also Yanis is a co-author here. So the outline of today is first, I'm gonna provide some background information on proton radiation therapy because I believe it's a new topic for most of you. And then I'm gonna compare robust optimization versus the K-adaptability and explain in details what K-adaptability is. And then finally, I will show the results and the conclusion. So proton radiation therapy is a type of cancer treatment. The idea is very simple. So we have a source of proton, and this is a proton. We shoot this particle into the tumor. The proton is going to deposit energy, and it's going to trigger necrosis of tumor, and hopefully the tumor dies. And in reality, of course, we don't only shoot the protons in one direction, but in multiple directions. So that's how proton therapy works. And speaking of the optimization, what we're trying to optimize is what we call dose distribution, which is basically the energy distribution within this patient. So we represent a patient's anatomy using a digitalized image, for example, CT or MRI, and this digital image is discretized by voxels. So you can think of this image is made of multiple small units called the voxels, and we can represent like organs and structures by a subset of the voxels. So for example, on this image, you can see there's a black contour here. It represents the target, and it is red here because we have a lot of energy deposited in this target region. And outside of target, you can see a gradient of color. It means we have less energies deposited outside of the target region. So the goal of treatment planning in radiation therapy is to optimize the dose distribution and also the number of protons that we shoot from each direction so that the tumor receives enough damage while we save the normal tissue as much as possible. So we want to keep the tumor region red, while outside we want to have it green or blue, as cold as possible. So this is the optimization problem right here. We have two decision variables. The first one is the vector x. It represents how many protons we shoot from each direction or trajectory. And the d represents the dose distribution. So how much dose each voxel receives. The objective is a weighted sum of individual objective functions, FIs. So FI can be, we try to maximize the average dose within the tumor. And this is the constraint. So these are the criteria that have to be satisfied. For example, we can say the maximum dose in the brainstem has to be no more than 30 gray. The gray is a unit of the energy we have here. And what I want to emphasize, and that's the most relevant thing of today, is this equality constraint. So we use this equality constraint to build a linear relation between the dose distribution and the number of protons from each direction. So this D matrix basically it tells you if we shoot one proton from each trajectory, how much energy that proton will deposit. So anyways, we can calculate this D matrix physically using Monte Carlo simulation. And finally, once we have everything, a medical physicist will play with the parameter, the weight here, until he or she finds a good dose distribution. So that's the nominal version. There's no uncertainty yet. But in radiation therapy, there are different uncertainties in this research. We focus on the range uncertainty and the shift. The range represents how far a proton will go. The reality is we never know how far a proton will go, even if we know the medium the proton goes through, because this physics interaction is stochastic, and the shift means there can be a mismatch between the planning day of the patient. So the patient will lay on the couch. We take a picture of this patient and we make a treatment plan. And in the next day, when we treat the patient is gonna lay on the couch again, but there can be a slight difference between the positions. So that's the shift. And these uncertainties yield uncertainty in the D matrix, the capital D matrix. And these uncertainties can significantly compromise the delivered dose. So the target coverage can be compromised. Also, we can deliver unnecessary dose to the surrounding normal tissues. So in radiation therapy, we use robust optimization as a common technique to account for the uncertainties. So what we do is we create a discrete uncertainty set. So we have the nominal image here, and then we can add anticipated uncertainties. For example, I think, okay, this proton will have an overshoot, which means it will travel 3% extra, for example, than what we would expect. And then we can have multiple scenarios to represent the alternative reality, and then we do a robust optimization to optimize the worst case objective. But robust optimization is good, but one downside of it, one trade-off of it is that if it considers too many scenarios, the solution can be mediocre. So to that end, we wanted to apply this K-adaptability approach to this robust optimization problem. So instead of preparing one solution to account for the entire uncertainty set, we would like to prepare K solutions. And each of the K solutions account for a subset of the scenarios. So therefore, each solution will be less conservative than that solution that accounts for all the scenarios. And then when the uncertainty scenario realizes, we just pick the best solution to implement. So in the end, we can achieve a better objective value. One thing I want to mention is that normally K-adaptability is a two-stage problem. Namely, we implement a solution before the realization of the scenario, and then we implement another solution after the realization. But here, in radiation therapy, it's only a one-stage problem. So we only implement solution after the realization of the scenario. Okay. So anyways, the crux of this problem is to find the optimal scenario clusters that induce the maximum objective value. But this problem is computationally intractable because there's just tons of ways to partition those clusters. So for example, if I have 50 scenarios and I want to cluster them into 25 non-empty groups, there can be 10 to 42 ways to do this. So it's like, yeah, you cannot really like solve this problem exactly, let alone the optimization problem of radiation therapy is also very time consuming. So therefore, an efficient heuristic is needed in order to implement this K-adaptability approach to radiation therapy planning. So a simplified workflow is that we create the scenarios and we cluster the scenarios in a good way. So we end up with K scenarios. And for each scenario, we just create a robust solution. And upon the realization of the scenario, we pick the best plan and then we treat the patient with this plan. Now, of course, it's not this simple. How do we do the clusters? So first, let's define what is a good cluster. So for us, a good cluster is the cluster that contains similar scenarios so that we think they would lead a better solution. And how do we measure the similarity between scenarios? We measure it based on plan performance, which is objective value on the uncertainty scenarios. So let's say if I have 3 plans, if I have 1 plan and I have 3 scenarios, and these 3 scenarios are also, this plan works very well on these 3 scenarios, and we just say these scenarios are pretty similar. So let me give you an example. So here, let's say I have 6 scenarios, and those blue scenarios represent a shift in the X direction. So I have 1 millimeter shift, 1.5, 2 millimeters, and the orange scenarios represent a shift in the Y direction. And then for X and the 1.5, I create a treatment plan. For Y 1.5, I create a treatment plan. Then I do the assignment. So for to each scenario, I assign a plan. And this assignment has to maximize the objective on the scenarios. And what would happen is that the plan created for X shift will be assigned to the scenarios generated with X shift. The plan created for Y shift scenario will be assigned to the Y shift scenarios. So, and in the end, the scenarios that gets the same plan go to the same cluster, and that's how we do the clustering. And to do the assignment, we use two mixed integer optimization problems. That is how they look like. So in simple words, the first problem optimizes the worst case scenario objective, and the second one optimizes the average objective values subject to the optimal worst case objective value from the previous problem, so that in the end the assignment is a robust Pareto optimal. Okay, so this is the algorithm, but too much information. But the input of the algorithm will be the uncertainty scenarios, and what it does, it's gonna find the best found combination of K solutions. So it's gonna find, okay, if we only allow one solution, what's the best? If we only allow two solutions, what are the best two solutions against this uncertainty set, and so on and so forth, until the size of the uncertainty scenario. And it has two phases. So basically, in the first phase, we do the assignment. So we get to the clusters, and then we run a robust optimization on each cluster. We add the new solutions to the solution pool, and we do it again until it reaches equilibrium in the cluster and the objective value. And then in the second phase, solution redistribution, after we generate solutions, we have a complete solution pool, and we run the assignment again in order to achieve a better, at least no worse objective value from compared to what you get in the first phase. So that's pretty abstract. So I will give you a toy example of 4 scenarios. So here I have 4 scenarios in the uncertainty set. We're gonna first create a nominal solution for each scenario. So in the solution pool, I have 4 solutions. And then we start generating solutions for k equal to 4. So in this case, in this phase, we allow 4 solutions, but nothing will happen because each scenario will just get their own nominal solution. So no clusters, new cluster will be formed, therefore no new solutions. So we go to k equal to 3. We do the assignment. We'll get a worst case objective value, and then we have 3 clusters here. So you can see, for example, scenario 1, the 4 are assigned to plan 1. Scenario 2 is assigned to plan 2. Scenario 3 is assigned to plan 3. And then once we have the scenarios, we create a solution for each individual cluster. And because this 1, 4 cluster is new, it has never appeared before, so there's a new solution, solution 5 created. And then we add solution 5 to the solution pool, and we do the assignment again. And because solution 5 is created for a cluster that consists of scenarios 1 and 4, it will be assigned to them. And the same from before, 2 is assigned to 2, 3 is assigned to 3. So no new clusters. The clusters are same from the previous iteration. But since the objective values in these 2 iterations are not quite the same, because here the solution 1 is only created for solution scenario 1. So in the end, it should provide a less worst case scenario objective than solution 5. So we will go to the third iteration, and then we reach the equilibrium, and then we go to k equal to 2, then k equal to 1, and in the end, let's say we get 7 solutions in the end, and then we go to the solution redistribution phase. We do the assignment again, and because in this phase we have 7 solutions, so the worst case objective value for each k will be no worse than what we obtain here. So for example, for k equal to 3, we are only selecting 3 solutions from 5 solutions, whereas here we're selecting 3 solutions from 7 solutions. So we can potentially achieve a better objective value here in the redistribution phase. Okay, so that's the algorithm. And then let's move on to the data. So we tested the K-adaptability on 5 head and neck patients. So they had tumors in the head and neck region. And we want to achieve 57 gray in the target. The objective is to maximize the worst case minimum dose in the target across all the scenarios. We have 57 uncertainty scenarios, which are combinations of 3 different kinds of range uncertainties. So no range uncertainty, 3% overshoot or undershoot, and 3 millimeter shift. and we shift the image along 1 or 2 coordinates. So like if we shift along X coordinate, there will be just 3 millimeter shift in the X coordinate. If we shift in both like X and Y, then there will be square root of 3 in the X and the square root of 3 in the Y direction. Okay, so in this project, we first want to evaluate how much we can improve by employing this K-adaptability heuristic compared to the conventional one solution robust optimization. And then we want to see how efficient is our heuristic compared to other clustering methods or the variance of our heuristic. So versus the conventional robust optimization. So the maximum improvement in the objective value, or like what I say minimum dose here in the target, on average is 4.5 gray. So it's like 8% to the ideal value we would like to achieve. But in radiation therapy, this is quite a lot, although 8% doesn't look a lot. So that's a very good improvement. And if you see this comparison in dose distribution, the gray area, bright gray, represents the target. You can see the conventional robust plan has pretty cold dose distribution here, while what we get from the K-adaptability is much more red, so better target coverage. And to demonstrate the efficiency, we compare the K-adaptability heuristic to variants of it. So the first variant is for each K, the solution pool starts with the nominal solutions. So it's a different starting point. And another variant generates the solution from ascending order. So our heuristic generates solution from the size of the uncertainty set to 1, whereas in this variant generates solutions from K equal to 1 to the size of the uncertainty set. So we wonder if the order of K matters. And then it's the K-medoids method. So basically, it clusters the scenarios based on the L2 distance between the capital D matrix. So it's a completely different thing because these 2 variants, including our heuristic, cluster based on the objective values, whereas here it clusters on the L2 distance based on the D matrix. And we look at 3 matrix. So the first one is the objective sum over K equal to 1 and 10. So it will be the area under here. We look at this matrix because it represents how good an objective a heuristic is at the early case, because in the early case we expect more fluctuation. In the later case, the objective value goes to the maximum you can achieve anyways, so there's less fluctuation. And the second metric we look at is the saturation K value, so which is the K, the earliest K where the objective value doesn't grow anymore, reaches the maximum that's possible. And the smaller this value is, the better this heuristic is. And third, we evaluate on the time cost, so how much time it takes to finish running this heuristic. So in simple words, speaking of objective value, so the sum from K equal to 1 to 10, and also the saturation K value, our heuristic, so the top row is the best. So completely beats the one variant. So the ascending order variant and the K-midoids. So it's like 48, 15, whereas they're like 16, 46, 47, and the saturation values are also pretty much worse. And it's slightly better than the variant where the initial solution pole is fixed. So you can see it's like 0.8 better in the sum on average, and 1.6 better in the saturation. Okay, and but speaking of time-wise, our heuristic is 22% faster than the comparable variant. So the advantage of it is also like it's fast. So that's the result. Conclusion, we developed an efficient K-adaptability heuristic for discrete uncertainty set problems, and we tested on proton robust planning problem. We observed significant improvements compared to the conventional one solution robust optimization. And then our heuristic could obtain better objective values and also faster than other clustering methods. And another takeaway is that although we developed this heuristic for proton therapy planning problem, it is also a generic problem that's applicable to other domains where they use a discrete uncertainty set. Okay, so that's the presentation from me. If you have any questions, please feel free to ask.